You really weren't kidding. That really wasn't saying much. So, okay. So, out of curiosity, how many people in here have written a programming language before? Show of hands. 1, 2. Most people are kind of going, kind of, sort of, maybe. Interestingly enough, Danes have been responsible for a lot of really interesting things going on in the computer science world. Of course, Bjarne Stroustrup does C++. Anders Hallsberg, and I know I'm mangling the Danish here, but Anders Hallsberg creates C#. Eric Meyer is responsible for a lot of the reactive stuff. So whatever it is you guys have in the water here, or the beer, or whatever, keep drinking it, because it's working. So if you're interested in languages, well, let me back up. Why would you be interested in building languages? Because this is not always considered a trivial task. For a lot of people, this is a very, very dark art. In many cases, the act of building your own language is one of the things that will frequently set you apart from a lot of your peers, to actually have created something. And even in some cases, if it is merely a trivial language, the act of having created a language that other people can download and make use of, and potentially, like, even maybe ship one thing in production, et cetera, et cetera. That's not something that your average computer scientist can claim. In many cases, even if you never go that far, if you never actually build something that is useful enough for somebody else to learn, it can be of direct benefit for you as an individual. For starters, this is one of the classic problems of computer science. When you really boil it down, this is one of those areas that a lot of students will study while in university. They will hear a lot of the theory. It's really one of those subjects that, particularly if you're like me, for example, and you were not a computer science student in university, my degree is actually in international relations. And if you want to learn some of the algorithmic approach, if you want to learn some of the various terminology, the whole 9 yards, it's an extremely good exercise to go through building your own language, because you'll be forced to come face to face with a lot of that stuff that you may or may not have missed out on. Even if you were a CS student in university, let's be blunt. In the age of 20, you're more interested in beer than you are in abstract syntax trees. So you may not remember it. It may not have stuck. And going back and revisiting it can often be a useful way to help dredge some of that stuff that you kind of sort of learned and go, oh yeah, I kind of remember the professor talking about that one night after a really, really long session of drinking. Anyway, the other thing is, as somebody who uses these tools, it can often be extremely helpful to have some practical familiarity with actually trying to build these tools. In many cases, for example, I remember when C++ first got templates, generics for those of you who never programmed in C++, that stuff is magic. I mean, seriously, when you sit down and you start thinking about all the things that a compiler has to do in order to be able to understand, to be able to parse, to be able to put together the models at compile time in order to be able to do the code generation, it's no surprise that people have discovered in later years that C++ templates are in fact themselves Turing complete. You can actually write code that will be executed entirely in the time frame of the compiler, and will then yield effectively constant results when you actually run the code. There's some really interesting research that's going on. And I'm not saying you should do that, don't get me wrong. But the point is, there's a tremendous amount of complexity there. By comparison, one of the features that was often touted as really, really interesting and complicated at the time was exception handling. The idea of setting up a block and things that would pop stack frames. And yeah, once you understand how a lot of this stuff gets built, that's boring. That's really just popping frames off the stack, having a particular catch in place, a little code to check whether or not this type is of the appropriate type. If not, keep popping stacks. That's boring. Once you understand how the tools that you use are built, you can begin to appreciate some of the complexity that goes on in there, and this can help guide some of the decisions that you will make later on as well. If, for example, you are trying to decide whether or not to use exception handling in a particularly performance-sensitive part of the code, if you understand what the compiler will do with an exception block, if you understand to a lower degree, if you understand what the JVM will do with that exception block, you can make much more reasonable decisions regarding whether or not to use an exception here to help clean up the code, or whether you want to do something a little bit more exotic but a little bit more performance friendly. Interestingly enough, by the way, I remember, this was probably about 10 years ago, sitting in a room with a senior Java architect who argued that you should never actually use the plus operator for strings in Java because that actually creates a whole bunch of string temporary objects, blah, blah, blah. And I said, no, that's not true. He's like, no, it most certainly is true. I said, no, it's most certainly not true, and I can prove it to you. Let's create a small demo. Let's compile it to JVM bytecode. I'm going to look at the bytecode and show you that, in fact, the compiler transforms this into a series of string buffer calls. He still didn't believe me. You're looking at the code there. You can see string buffer there on the stack. He's like, no, those get turned into string objects later. I'm like, no, they really don't. And by the way, you're going to vote Trump in the future, aren't you? But it also has, and to be honest with you, no, I didn't stay in touch with him, so I don't know if he did vote Trump or not. It also turns out, though, that a lot of the tools and tactics and techniques and so forth that you will learn when thinking about building languages are useful outside of the language construction process entirely. For example, if you've ever had to think about doing certain kinds of web validation, on the one hand, you could use a regular expression to do some kinds of string validation, but then you have two problems. You have the original problem and then the fact that you used a regular expression to try to solve it. And inevitably, a regular expression is going to turn into a parsing problem. Or when you start looking at the construction of software, when you look at compilers, you will see that there's a very well-defined pipeline, and you can start to see how that could in fact be used in a variety of other cases, particularly, for example, if you've ever done ETL, extract, transform, and load. That is fundamentally a compiler problem. Extract is a certain form of parse or ingest, and then you need to do some sort of transformation, which means particularly if you're pulling from multiple sources, you want to have some sort of single source of truth from which you can then do the transformation into some other format by which then it gets loaded elsewhere. Folks, that's basically what a compiler does. Consider, for example, you have some bit of code that needs to be some basic state machine, right? Classic state pattern, right, where I need to track, for example, the vending machine, the states that go on inside of a vending machine. Somebody puts a coin in. Do they have enough money? Yes, no. Okay, then we need to move them into another state where money is there, but it's not enough. And then they continue to put more money in. And at what point do we have enough money? We need to keep track of that in some sort of accumulator. And of course, if they push the coin reject button, meaning give me all of my money back, well, obviously we need to check what state we're in, et cetera, et cetera. As a state machine gets to be more complicated, this becomes really, really tricky to try to represent in if-else statements or giant switch block or something along those lines. Inevitably, we start thinking about how do I more formalize this particular state machine. And that's where we get, for example, the state pattern, or we get various state machine code libraries and so forth. Let me ask the question, why has it never been generalized into a programming language, period? Why can I not say inside of my class vending machine, when state change happens, here's a block of code to execute. When state change happens, here's a block of code to execute. Why can't that be a first-class concept inside of a programming language? Traditional business rules. Anybody ever tried to rent a car in the United States? It has to be one of the most bizarre things you will ever do. I kid you not, I had a conversation once with a Hertz rental car agent, and I said, okay, well, I need to rent a car Monday night. And she said, okay, well, what time's your flight coming in? And I said something like 5 p.m., 1700 for those of you in the audience who, don't speak American. I get in about 5 p.m., and she said, oh, we don't have any cars available. And I said, really? You don't have any cars available at that time. What she meant was, there were more reservations than they had cars. And I said, oh, okay, well, what can we do? Because I really do kind of need a car. And she said, well, you know what we could do? She said, why don't we set the reservation to begin at 11:59 p.m. on Sunday night, the night before, and then when you get on board your aircraft, like before you go to bed on Sunday, call in and say that you're going to have a late pickup, and that'll buy you another couple of 4 hours. And then because you're a Hertz Gold member, you automatically have an 8-hour window anyway, so that'll actually push you well into Monday. She basically figured out how I could request the car on Sunday, but pick it up on Monday, even though there are no cars available on Monday, which means somewhere in the world, some guy got to the lot and said, where's my car? And it's like, oh yeah, see that guy with long hair over there driving out of the lot? How do these kinds of exceptions and exemptions and edge cases and so forth, how do they filter through? Who sat down and said, yes, this is how the system should behave, and this is what we should allow and shouldn't allow, and so on and so forth, so on and so forth. Can you imagine? Think about airline tickets, for example. If you try to fly from the US to Europe, if you fly out on a Monday and fly back on a Friday, that's business travel, and that's going to cost you like $3,000 US. But if you come back on Sunday because there's a Saturday stay, now it's only about $2,000 US. Unless you leave from Sacramento Airport instead of San Francisco Airport, because Sacramento to San Francisco, that's actually going to be another $500 cheaper, even though it's an extra plane. What? None of this stuff makes any sense, but there are all these arcane business rules that need to be captured. And there's one of two choices here. Either A, you can sit there staring at the screen and look at every possible if, else if combination for all the possible variable points and get it all correct. And of course, you will write unit tests to cover every possible edge case, right? Go like this. Yes, of course you will, because you are a good programmer. And you will never discover an edge case that actually behaves correctly in the software system, but is actually incorrect according to the old legacy system that you're supposed to be replacing. That'll never happen. Or we can think of ways to capture these, again, as a first-class concept inside of a language. Declarative statements as opposed to imperative executional stuff. And it may sound that I'm sort of advocating in a very, very subtle and snide manner for something like a functional language, because functional languages, they use declarations, blah, blah, blah. Functional language isn't really going to help solve a lot of this stuff, because a lot of this has to do with actual regression and permutations and so forth. This is much more the realm of a logic language like Prolog, which Prolog generally isn't classified as a functional language. Yeah, if you dig down deep enough, yeah, there's some functional stuff there. But it's actually much more appropriate to the idea of testing a wide variety of possible permutations and evaluating and getting a result back. The logic languages, of which Prolog is the granddaddy. And there's a whole bunch of computer science problems we haven't even begun to try to solve. Concurrency, it is fair to say that concurrency is not a solved problem. Thank you, Lightbend and Akka and Streams and all of that stuff. We will take your guidance under advisement, the whole actor model, etc. But that doesn't solve concurrency problems. It helps mitigate them, it helps maybe hide some of them, but there are still a whole slew of problems that we haven't yet addressed. User interface. How many of you are still building UIs using a programming language like Java? Have you ever wondered why that was a good idea? Why don't we have a language that actually speaks HTML, CSS, and JavaScript, or some derivative thereof, as a first-class concept? Why don't we have a language that actually has notion of web, pages, HTTP, session, however you want to think about the web? Why don't we have languages that deal with those as first-class concepts? Because in many cases, we're still very firmly rooted in the idea that it must be done in a general-purpose programming language that must start from very basic object-oriented principles like class. Why don't we have page? Why don't we have component? Why don't we have first-class concept? Sir? Do I know about Vaadin? I know of Vaadin, yes. You've got all of that stuff, but even there, Vaadin is a library sitting on top of a general-purpose language. Stop. Let's you and I have that debate outside over beer, right? Because at this point, then somebody else says, well, what about Smalltalk? And once somebody brings up Smalltalk, I mean, that's kind of like the Hitler of computer science. Once somebody says Smalltalk, the conversation is just bound to devolve, right? So, no, there is a lot of really interesting research going on. For example, there is a language called OPA, which is coming out of, I forget, one of the European universities, if I'm not mistaken, that is trying to come up with a unifying model. In the JavaScript world, there is a similar effort that's more, again, library-esque than language-esque called Meteor, which says, let's do JavaScript all the way down the stack, from the UI all the way down to Mongo at the library level. There are people who are researching this, don't get me wrong. But so much of our energy in the Java world has been about building libraries, right? Let's build JPA, let's build Hibernate, let's work with the Java syntactic limitations and try to find something that works. As opposed to, let's actually break away from the Java syntax base and try something different. Let's actually try building something that addresses the problem directly. This is the space that a lot of the DSL movement went about 5 to 10 years ago. And unfortunately, it kind of feels like it's petered out, which is sad to me. I kind of want to see it get some effort going, because DSLs were sort of assumed to be user-facing. They had to be user-facing, otherwise somehow it was a failure as an experiment. And I think a lot of the stuff that we could have done could have been much more developer-facing, right? Application security, the idea of being able to issue constraints as part of my programming language, as opposed to having to do that either in terms of which objects I put in place in front of this thing, or which declarations I make as a part of configuration. I kind of would like to see that exposed as a part of the language itself, personally. And again, I brought up DSLs, right? Both the external DSL, that is to say, let's create our own standalone language that compiles, it's its own tool chain, etc., as well as the internal DSL. We've seen a lot of fluent libraries emerging. Spring has been doing a fair amount of that. If you were in the room earlier as we were looking at Spring Boot, we saw Spring uses several fluent libraries in an attempt to, within the limitations of the Java syntax, make something that reads relatively fluently, something that reads relatively like English. But we still want to continue going down this path of thinking about programming languages for programmers' use. Why not start with Java as a base language and perhaps extend it? Why not take Kotlin or Groovy or one of these other languages and extend that in various ways? And this is what we're seeing a lot of these recent generation languages like Kotlin and Groovy, like Scala, are trying to provide hooks and endpoints so that people can, in fact, try to take this and extend it in ways that may not have been originally anticipated by the language's creators. There's a metric crap ton of tools available to you that all have some relevance to the whole language's space. I mean, the build tools, for starters, they're interesting examples of, as well as interesting utilities. Gradle is a perfect example here. Gradle started out as simply a Groovy library wrapper around Maven, and then sort of went from there and gotten to the point where I can express in a dozen, maybe, lines of Gradle what before required how many pages of XML in terms of Maven. Don't get me wrong, Maven was wonderful, Maven was great. No, it wasn't. It was terrible. Whoever decided that XML was a great language in which to express a build, well, actually, we know who it was. It was James Duncan Davidson, and he started it with Ant. And he has since apologized, by the way. He actually apologized in Mike Clark's book from about 15 years ago. JDD freely admitted that the only reason he used XML was because he didn't want to write a parser. Now, if you could go back in time, teach JDD how to write a very simple parser so that you wouldn't have to live for 15 years with pointy brackets poking your eyes as you're trying to debug your build, yeah, I think he's hiding out in Greece these days. I'm not sure. Virtual machines, database query engines, code generation tools. There's a whole bunch of output template engines. There's a whole bunch of things that are available out here in terms that, relate to, are part of, inspired by, can be used in, around this whole notion of compiler construction. We see static code analysis tools are really starting to emerge and find their footing. Findbugs, which has been around for the better part of a decade, I think, maybe a decade and a half at this point, as a way of looking over your Java code and identifying potential errors. As a matter of fact, this is going back a ways, but I believe it was for the JDK 1.4 release when Bill Pugh, who is the researcher who is behind Findbugs, he actually ran it on top of the JDK 1.4 swing source code and identified 4 concurrency bugs that had never been reported. Because a static analysis tool can actually do a whole bunch of permutation kinds of investigation that you as a human being would only ever be able to spot maybe if the gods were aligned correctly. Findbugs found 4 of them, which had been lurking in Swing for, let's see, was at least 2 JDK releases, because Swing came out in 1.2. Good stuff. So how do you do it? How do you create a language? Assuming you're now inspired, you're on fire, you're not just feeling heartburn and want to leave because of that. It was a good lunch, by the way, though. I don't want to imply that that was the lunch's fault. If you want to create your own custom language, there's 4 phases that you need to think about when we talk about a traditional compiler pipeline. Now, don't get me wrong. You do not get to walk out of here and put language designer on your CV and immediately start applying to Oracle to go work with Brian Getz on Java. There's going to be a bit of a gap between what we talk about here and what Brian does every day. But when you look at the JDK source code, when you look at the source code for Java-C, you will find these 4 basic phases as a part of any compiler, any interpreter, whether it's Ruby, whether it's Swift, whether it's Java, whether it's C#. As a matter of fact, for those of you who haven't spent a lot of time in the .NET world recently, Microsoft has open sourced the C# and Visual Basic compilers under the code name Roslyn, R-O-S-L-Y-N. And so if you've ever looked at C# and thought, wow, that property syntax makes so much sense, I wish we had that in Java. Well, C# is open source, so you can see how they did it, and Java is open source, so you can actually get a hold of it and make your own changes. ... I'm going to leave you to infer the rest. Lexing and parsing, first step. That's actually the transformation of source code into some intermediate representation, frequently known as an abstract syntax tree, and I'll go over some of this in more detail. From there, we analyze the AST to make sure that all of the code makes sense. Are you, in fact, able to invoke the method that you're trying to invoke? Does that field exist that you're trying to reference, et cetera, et cetera? And then finally, once I have that intermediate representation, what do I do with it? I can either take that AST and put it out in some sort of written executable format, or I can actually walk the AST directly, and that's what we call an interpreter. Lexing and parsing. These are 2 separate phases because they actually, it makes sense in a lot of cases to break these 2 up, because in some scenarios we can identify some errors very early on and not have to complicate the later part of figuring out whether or not all this stuff makes sense. The intermediate representation, I already mentioned that. Frequently it will be in the form of a tree, but for some of your more higher end environments, there will also be a secondary intermediate representation referred to as IR, which will often have some assembly-like characteristics to it. Depending upon the degree of abstraction away from the underlying hardware, Sometimes this will be very, very abstract, almost JVM bytecode-like, and that would be known as a high intermediate representation. In some cases, it's very, very close to the hardware, almost to the point of being an actual assembly language. That's known as a low intermediate representation. The problem with high IR is you don't have any real opportunity for optimizations based just on the abstract nature of it. The problem with low IR is the fact that you in some cases can be too close to the target output. So for example, optimizations that may work for an ARM processor wouldn't work for an x86 processor and vice versa. So there are a lot of toolkits that will actually go from AST to high IR to low IR and then eventually into target output. And bear in mind that there can be a number of phases that are a part of each of these. So as a part of the analysis phase here, for example, there will frequently, if you look at the Scala compiler, there's something like 17, 20, 25 different phases they do, all lumped under this umbrella of analysis, where they are looking for opportunities to unroll loops, they're looking for opportunities to propagate constants, they're looking for opportunities to do any kind of optimization they can possibly identify. And each of those is a separate phase in that process. As a matter of fact, if you go down this path, and if you're using the Scala compiler as a part of your project, the Scala pipeline actually has opportunities for you to plug in your own optimizers into the compiler pipeline. So if you've got your own phase that you'd like to introduce, go for it. You just have to tell them on the command line, this is the class, you have to obey the appropriate interface, you obviously have to understand what they're handing you, you have to understand what to produce to push back out, but you have the opportunity to engage inside of the Scala environment. And as a matter of fact, how many people here program in Scala, just out of curiosity? A couple of hands. If you ever looked at the Scala annotation that basically says, I want to treat this Scala class as a Java bean, generate getters and setters and so forth, so that it would be friendly to things like Spring, for example, that rely on getters and setters to indicate a property, etc. That annotation is picked up by one of those phases, and that's when they generate the Java bean specific syntactic methods, etc., to make sure that this will in fact be beanish. And that's just done as part of an optimization phase, as part of the analysis. And then lastly, again, you can either execute the intermediate representation or the AST directly. This is what Ruby does. When Ruby parses your code, it puts it into basically puts it into a giant tree and then just starts executing the nodes in the tree. This is what the node interpreter does, actually. The node parser parses all of that JavaScript source, turns it into its own internal bytecode format, which is more of a low intermediate representation, and then begins executing that format. Or we could code gen. Now, the idea here behind code gen is whatever output you get, it should be directly executable. Now, we have to put quotes around that because normally directly executable would mean we're putting something out that is machine specific. It's a portable executable file if you're on Windows. It's a Mac, and I suddenly have blanked. It's not COF, it's some other file format that the Mac adopted that's based off of COF. But, for example, a CLR assembly or a JVM jar file, those are not directly executable. You have to have a virtual machine in order to execute them. Well, okay, if you're talking to a bunch of people who are from the Java environment, a class file is basically directly executable. You all know what to do with a class file or a jar file. We can assume that. There are, however, some languages, and this is becoming much more popular in the JavaScript world, that will do what are called transpiling. It's not compiling. It's transpiling. We're actually going from source to source. So in fact, we're taking source language like CoffeeScript, we're running it through what for all intents and purposes looks like a compiler, but the executable that comes out the other end is actually JavaScript, not something else. Now, the reason why JavaScript is, of course, it is the ubiquitous language that every web browser supports. Because the idea of having one language that runs inside of every browser, that's just ridiculous. That'll never work. Right? I mean, it's not like anybody's ever tried to do that before, maybe with actually a bytecode format, you know, and the name is too long, so we'll just take the first 4 letters of it. And Interestingly enough, how many of you have heard of WebAssembly? Yeah, about a half a dozen hands coming up. For those of you who haven't, WebAssembly is the latest effort to introduce what is effectively an executable bytecode into browsers, and it's inspired by asm.js, which is, get this, it's a JavaScript library that is intended to look like assembly language. There is a tool called mscripten, emscripten, mscripten, that is a C++ compiler that will compile your C++ source code into asm.js output so it can run in the browser. Now, if your C++ code actually uses OpenGL method calls, the asm.js and the mscripten compiler will actually silently transform those into WebGL. So yes, you can take your old Doom source code, compile it, and run it in the browser, just like you did back in 1995. Wee-haw! It is now a complete loop. We have now gone to make the browser into an operating system, and WebAssembly is the attempt to codify ASM.js that it will work across all the browsers. And I think it was earlier this year that actually reached a working draft status. The WebAssembly specification is available, and you can in fact compile something into WebAssembly modules, load it, run it, et cetera, et cetera, et cetera. Yeah. But applets, no, they're dead. We would never want to do applets. All right. So, going through those 4 phases in a little bit more detail. Step 1, Lexing. This is the first pass. This is generally where we will take your source code and we will run through it to make sure that all of the basic atoms are there, right? As we go through here, this is where we start identifying keywords as opposed to identifiers, as opposed to constants, strings, etc. This is not the point where we are trying to determine whether or not your line of code makes sense. This is just whether or not your line of code even passes a simple sniff test. Did you in fact typo something? Did you forget to put an end quote on the end of the string? Did you forget to put some sort of terminator on the character constant, et cetera, et cetera? This is effectively feeding into the next stage, which will be parsing, which will determine whether or not your collection of things actually makes sense. From a natural language perspective, this is, are you using words that I recognize in my language? Okay? So input is the standard character stream. Now, interesting branch of CS speculation, do source code files always have to be streams of characters? There's a number of companies that have actually explored the idea that maybe we really want to get above the notion of ASCII text as a programming language input format. Maybe we would like to use something a little bit more sophisticated. There is a company in Bellevue, Washington. It actually was started by Charles Simonyi, who is one of the well-known old Microsofties. And the company is called Intentional Software. And they've been going down this particular path of let's try to do some alternative source representations. Intentional at one point, I think they just got reacquired by Microsoft. They got spun out about 10 years ago. They just got rebought. So I don't know if a demo of their software is available anymore. But at one point, they actually had a demo where you could write code using music. I'm not kidding. You could actually use musical staff notation as an input format to your source code. But think about this for just a second. If you deal with people that, for example, are math science folks, so for example, I taught a class out in Denver, Colorado to a group of folks that do a lot of oil and gas drilling, and they've got some old mathematical formulae that were written back in like the 1950s in, of course, Fortran. Now, how many of you feel comfortable enough with Fortran that you could rewrite Fortran in Java and get it right along every edge case? Show of hands. 1. You did Fortran back in the day? And you remember all of it? It's not that big. Okay, all right, we're going to test you later. And by the way, millions of dollars are riding on this, because if you get any part of it wrong, people are going to go drilling in your backyard as opposed to in a field where there's actually oil. So no pressure. But think about the fact that the Fortran language was originally created to capture formulae. What if we could just capture it directly? What if, for example, there is a markup language called MathML? What if that could be your source input format? Just feed directly from MathML into the compiler, which would then emit bytecode out the other end. That's kind of intriguing. So we start with some kind of format. What comes out of the Lexer is a stream of tokens. These are typically slightly higher level elements above and beyond the actual source code. So for example, public would get transformed into a keyword token. And if you have a 45.0, that would get transformed into a numeric token, et cetera, et cetera. This makes it easier for the next step to be able to determine whether or not these are in fact in the right order, if they're in fact in the right place. Here, for example, you can see I have public, which is a keyword, and then public, which is probably a typo, but at this point we don't know, because that is in fact a legitimate Java identifier. You could actually be using that as a variable name. I would love to see the comment around that to explain what exactly that thing is, but it is a legitimate identifier name. We don't know if this is an error yet. If this is public static int public, okay, well then that's legit. That's an identifier name. If it's public static void main, okay, now we have a problem, because in fact this identifier doesn't make sense in that particular place. And that's the job of the parser, to look at that stream of tokens and determine whether or not they're in the right place. Effectively, the parser then says, once we've determined that you are in fact using legitimate words for the language in question, do this string of words actually make a coherent sentence? The parser typically takes the Lexer's input format, that is to say that stream of tokens, and analyzes it to determine whether or not, in fact, this information is correct, determine whether or not this structure is correct. If I do have public void static main, is that acceptable, or does it have to be public static void main? Can I have the return type, or can I have static public void main? That's the job of the parser, to figure out what exactly is appropriate, what exactly is acceptable to this language designer's mindset. So here, for example, again, assuming you speak English, no, this is not my attempt to capture Danish, I swear. The first line there is, that's a Lexing error. Those are not English words, not even if Donald Trump says them, okay? The man has introduced some wonderful new words into our vocabulary, and we will love him forever for that, but that doesn't make them legit. Okay? Not until it actually shows up in the dictionary does it in fact qualify as an English word. Similarly, however, though, in the second line, those are legitimate English words that make absolutely no sense when used in that way. The first line is a set of Lexing errors. The second line is a set of parsing errors. Now, there's still a whole bunch of analysis that would yet need to be done. I can have public static void main, parens, curly bracket, and then say, okay, let's see, system.out.writeLine, parens. That's all legitimate Java syntax. That will parse successfully. It won't be until later in the analysis stream when we look at the AST that we determine that system.out does not have a method called writeLine on it. That method is called printLine. That occurs later. The parser's job is simply to say, is what I'm looking at, in fact, legitimate language construct? If it is, then I will go ahead and capture it in some form of an intermediate representation for later analysis. Now, as you could well imagine, trying to reason about all of the possible permutations that a language could in fact obey, this is complicated, and language designers will go back and forth. Do I want to try to write a parser by hand, or do I want to capture this in some larger construct? The folks that come into the latter category will create what's called a grammar. using a notation that's designed to try to make the grammar unambiguous so that there's no possibility for circularity and no possible weird paths through the language that will allow it to express something that you never intended, et cetera, et cetera. There's an attempt here to try to formalize the language. More importantly, if you can formalize it into a grammar, then in fact you can do some code gen out of it. I'll show you one of these in a little bit, a very simplified one. But usually it follows something that looks like this. EBNF is extended Becker-Nar form, and it's something that you will learn as part of your classic CS education. And here what I'm saying is that input consists of white space, an expression, and then white space. Okay? Now, why do I say white space on either side of that? Well, because I want my language to have some flexibility with respect to white space. If we start looking at the EBNF for Python, for example, we can't be quite so cavalier because Python will actually count the number of spaces or tabs from column 0 in order to determine indentation levels. F# does the same thing, by the way. As a matter of fact, a lot of the ML family prior to F# depends on indentation. We look at an expression which is a factor which can consist of white space, the multiplication, and the division, white space factor. Okay? And white space, we can see down there at the very bottom, by the way, consists of any number of spaces, tabs, carriage returns, or carriage returns, right? Remember, /n is the new line, /r is the actual carriage return, because technically those are two separate ASCII characters, and they get interpreted differently whether you're on Linux, or DOS, or Windows, or that. Anyway, all the usual white space characters that we're accustomed to, any number of them, that's what defines white space. So basically what we're saying is an expression is a factor times or divide a factor. And a factor is a term plus or minus a term. And then a term can actually be bounded by parentheses containing an expression, or it can have a negative in front of the expression, which would thus make it a negatory whatever. -1 is a perfectly legitimate expression. Or it can be a number, where a number is a digit followed by optionally a dot and more digits followed optionally by either e's for exponentiation and then another minus and then another digit and so on and so forth. This is all, of course, as part of exponential notation, and a digit is, of course, 0 through 9. Boom, any questions? The whole point of this is that effectively a term over here is either made up of other terms or ultimately it's made up of source characters that we can resolve back to, in this case, the ASCII character set. If you wanted to use some other input format, then you would have to have some other sort of constants here. But this is a formal way to describe what is effectively a calculator notation. Now, what we do is we take that grammar and we feed it to a tool who can then generate the actual code for doing all of the parsing. One such really powerful tool is called Antler. If you go back far enough, Antler actually, the name derives from bison, which is actually a GNU tool that in turn is from Lex and Yak. Get it? Yak, bison, antlers. Get it? Computer scientists really have no sense of humor, so just laugh so that they think they're funny. Otherwise, they'll stop producing tools. Okay? Antler is a particularly powerful tool. The guy who's been working on it, Terence Parr, it's completely open source. There are several books on it. As a matter of fact, there's references at the end of the slide deck. Antler can generate a lot of different source code. So the fact that Antler is written in Java does not matter to the individual who wants to create a C# language, because it will generate C# code, which the C# compiler can compile, pick up, and run with. It's only when you want to regenerate the grammar because you've changed it in some fashion that you actually need to run Antler. And in some cases, what you can do is you can skip the whole notion of a formal grammar and just take strings directly. This is what JDD did when he said, I want to use XML for Ant, because there are already some existing XML parsers. Let's just use that, which, again, depending upon the problem in question, can be a useful scenario. In some cases, if it gets really popular and people actually want to start doing imperative decision making, if this property is set, do this, else do that, XML doesn't really sit well there, unfortunately. But in many cases, I've known people who have actually used regular expressions to create parsers for very simple languages. I wouldn't recommend that either. Once your language reaches a level of complexity, your best bet really is either a completely custom from hand parser or one that was generated from a formal grammar. Okay? In some cases, we can duck the parser entirely and make use of language facilities. So if you've ever used Ruby's Rake, which is a build tool, you are using an internal DSL. That is built entirely using the internal facilities of the programming language. If you've ever used Spock from Groovy, that testing tool is entirely built using the Groovy language. There's nothing specific there. No, 15 minutes. I'm done at 3:20, am I not? 3:10? Oh, somebody lied to me. You said 3:20. All right. So let me bounce forward. Bump, bump, yeah, IR, whatever. Analysis, who cares? Analysis is no fun. Execution, you just turn it into bytecode. I should mention, though, Attila Zaghetti has been working on a library called Dynalang, specifically for the JVM. This would be an excellent target for your custom language, whatever you're working on. And particularly if you want to try to generate Dynalang AST and then execute it directly, it works very, very well as an interpreter. Again, you can also code gen, and if you're going to do that, there's actually an academic project called Soot, which is specifically looking at building JVM output, or of course, you've got your classic bytecode toolkits, ASM or BCEL. There's also the JavaSys library, which is really useful for taking existing code and transmogrifying it, modifying it. JBoss has been using it for years as part of their EJB implementation. But let me show you what this looks like in practice. So going back to that calculator example, I'm going to be using Antler, in this case Antler 4, because it's a little bit easier to work with. And the idea is that I want to build a very simple calculator that has a very, very simple functionality. That is to say, for each line up there at the top, I want to print the result of just that singular line. So I'm not trying to do anything super complicated. I'm not putting in functions. I'm not putting in, I'm putting in variables, but they don't have types. Everything's just assumed to be floating point, maybe 64-bit floating point, because again, that's what JavaScript assumes for all of its numbers. Everything is 64-bit floating point. You'll notice that I can capture them, A and B, and have simple variable usage so that that 5-line script there, well, let's see, 5 plus 6 times 2, 6 times 2 is 12, 5 plus 12 is 17. Okay, you can see 193, 17, 9, etc. Now, why would you want to do this? You could actually express this in the language itself, particularly if we're talking about Java. The point here is that you can take this as a simple example and build upon it. Perhaps your goal is to create a mathematical language, so to speak, that your business analysts can use to capture certain financial kinds of calculations. You want to build your own simplified spreadsheet with functionality that no spreadsheet currently has, et cetera, et cetera. It's a simple pedagogical example. We have some fairly simple Lexing requirements. We need to identify numbers, characters, the math operations themselves, and we need parentheses in order to be able to circumvent the order of operations. Antler will actually combine the Lexing and parsing into one G4 file. G4, G is for grammar, 4 is for version 4 of the Antler tool, so G4. Here we establish basically the tokens, mul, div, add, sub. They pretty much turn into what you would expect. ID is any, notice I just say any sort of alphabetical characters. I'm not going to deal with Java's ability to allow underscores and numbers after the first character, etc. An integer is just 0 through 9, any repetition thereof. New line, because new line is going to be my signal to print out this expression. And then white space, which basically here we use a built-in Antler primitive that just says skip. Skip any white space that we see showing up, period. Okay? Now, what that means is a calc program is made up of a series of statements, which are made up of a collection of expressions, which we need to evaluate individually. Okay? So here, the grammar, notice the name is labeled expressions. A program consists of one or more statements, where a statement is an expression followed by a new line, or it's an identifier equals an expression new line, or it's just a new line, which is blank. And then down here, expressions are made up of, again, multiply, divide, add, subtract, et cetera, et cetera. Now, what Antler is going to do is it's going to take that G4 file and it's going to build a set of utilities to parse that and then actually produce the tree as a part of the parse. The result of the Antler parse will be a tree, and it will generate a visitor-style interface that you can implement in order to be able to execute and/or code gen based on the results. So here, eval visitor is my implementation of that generated interface, the labeled expression base vinegar of type integer, labeled expression base visitor of type integer. And notice I introduce a map string integer that's going to consist of my working memory. So whenever I do a variable assignment or whenever I reference a variable, it's going to live inside that memory hash map. So here we see the assignment visitation. I just grab the context that's passed in, get the identifier. Well, that will give me the name of the identifier. Okay. Then I grab the value, which again could be an expression. A equals 5 times 5 is a perfectly legitimate expression, so I need to evaluate that. And then I just store it in the memory. A new line says just print whatever the expression is there. Here I'm going to visit a standard integer constant, which means just take the incoming text and turn it into an integer. That's what integer.valueof was invented for. And then if I have an identifier, we just go ahead and grab it out of memory. Otherwise, we assume 0. We don't want to have any errors if we can help it. And then multiply and divide, I simply look at the type of the expression and do the right thing. And then lastly, parentheses, just basically say I have an expression, evaluate it inside the parentheses. Lastly, I just construct the whole pipeline. Input stream feeding into the lexer, feeding into the token stream, feeding into the parser, feeding into the parse tree, and then at that point I take the tree, I slap a visitor on it, I say visitor, visit the tree, it prints, we're done, I'm out, goodbye.